Hello everyone, I'm Ben and this is Math with Ben, and today I'm going to finish up the second video on my real analysis series for section 1.1, which is the ordered field axioms. I finished up this section today. I've been reading while in school, so it's taken me a while to read, but it's a lot to chew on. So there are today I'm going to talk about, just what I finished. There are three main methods of proof. The first one is mathematical induction, which is something I already know how to do. I've learned it in a class. You assume a hypothesis is true, which you do for all proofs. You just assume whatever hypothesis you're using is true. And then for mathematical induction, you show the least number in a set is true. So like if your least number was 1, you show that the mathematical statement is true for 1. And then you show, using strong induction, which is the more rigorous and more useful version, you show that you assume that every statement from the least number to some arbitrary number n is true, and then you have to prove n plus 1, and that's mathematical induction. The second is direct deduction, which is something I don't know how to do, and I've learned a little bit about it. And the third is contradiction, which I do know how to do. You basically assume that the hypothesis is false. For all proofs that you ever do, you're going to assume your hypothesis is true. For mathematical contradiction, you assume that your conclusion is false, and you work through a proof until you get a logical fallacy or a contradiction in your math, and then by that you've shown that the conclusion is true. So what is a deductive proof? Well, first of all, you're going to assume that your hypothesis is true, right? And you do this for every mathematical proof. And then you work step by step to show conclusion is true. And every step along the way is justified. Now, this is, basically the same as, it's just a normal proof that I've, learned. So example, using deduction. 5, if a is in the real numbers, prove if a does not equal 0, then a squared is greater than 0. Well, the proof by the trichotomy property, which we learned last time, if a has to be greater than 0, or a has to be less than 0, or a has to be equal to 0. Now, we assume our hypothesis, so a does not equal 0. That is our hypothesis in this case. So case 1, we're gonna split this up into cases. Let me grab my pointer. Again, by the trichotomy property, a has to be greater than 0 or a has to be less than 0, right? Again, we assume that this is true because this right here is our hypothesis, right? P implies Q. So case 1, a is greater than 0. Multiplying by both sides by a, we get a squared is greater than 0, right? And then we're done. That's all it is, right? We've shown a squared is greater than 0 just by multiplying by a. We didn't have to change anything because this broke no algebraic laws this wasn't confusing in any way. All we did is multiply both sides by a. And, right, we have, like, a is greater than 0. If we multiply both sides by a, we get a times a is greater than 0 times a. And this is equal to a squared. And this is equal to 0. So, therefore, we get a squared is greater than 0. Nothing confusing there. Pretty simple. Case 2, a is less than 0. This means a is negative, right? If a is less than 0, it is not a non-negative number, which means it is negative. So if we multiply both sides by a, then a squared is greater than 0, right? This comes from multiplicative inverses, and we learned it up here somewhere. The multiplicative property in the order axioms, right? The multiplicative property in the order axioms just states if you're multiplying both sides of an inequality by a negative number, then the inequality flips. So if we go back down here, we have a as a negative number. So right now we have a is less than 0. If we multiply by a, this is going to be equal to 0 because 0 times any number is 0. That's just the multiplicative identity, right? And a times a is going to be a positive number. And this, again, a is less than 0, so you have to flip the inequality. So we're going to get a squared is, flip the inequality, is greater than 0. And we're done. Again, it's a really easy proof, and it's a really easy proof method. And it's pretty interesting to think about. And so here we have a definition. The definition of the absolute value of a is equal to, well, if a is greater than or equal to 0, then a equals a. If a is less than 0, then negative a equals the absolute value of a. This comes from, say you had negative 1, right? A is clearly less than 0. This is clearly less than 0. So to get the absolute value of negative 1, all you do is negative 1. And this by some of the multiplicative properties and by the algebraic laws we proved earlier with the first postulate. With the first postulate, we've already proved that this absolute value of negative 1 is going to be equal to 1. This just comes from negative 1 squared, right? So here's a remark. The absolute value is multiplicative. So this means that absolute value of AB is equal to the absolute value of A times the absolute value of B. Now, there is a proof for this in the book. I'm not going to go into it. It's, it's just something you just need to know is true. Not necessarily that important to prove. Theorem. Let A be in the set of real numbers, and M is greater than or equal to 0. Then the absolute value of A is less than or equal to M if and only if, that's what that IFF means, if and only if negative M is less than or equal to A is less than or equal to M. And again, there's a proof for this, and if you want me to prove it, I can prove it on a Instagram reel. On the Instagram, I think I'm going to start doing reels. I might actually post one today regarding functions or a cool proof that I've learned or something. So here we have another theorem. The absolute value satisfies the following properties. So this is just the absolute value of any number in general satisfies these three properties. So these are sort of more axioms. 1, the positive definite. For all A, that's what that upside down like capital A is. So for all A in the real numbers, the absolute value of A is greater than or equal to 0, with absolute value of A equaling 0 if and only if A equals 0, right? You can't have the absolute value of any number equals 0. It has to be 0. Symmetric. So the absolute value has to be symmetric. For all A, B in the set of real numbers, the absolute value of A minus B equals B minus A. And there, again, is a proof for this if you are confused at all, and I can go over that later if you would like me to. And the third property is the triangle inequalities. So for all A, B in the real numbers, the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. The absolute value of A minus B is greater than or equal to the absolute value of A minus the absolute value of B. And the absolute value of the absolute value of A minus the absolute value of B is greater than or equal to the absolute value of A minus B. So here we have an example that uses these properties, 1.8. Prove that if negative 2 is less than x is less than 1, strictly, then the absolute value of x squared plus x is less than 6. So by the hypothesis, x is less than 2 because x is strictly less than 1, which means it also has to be greater than less than for anything greater than 1. And then by the triangle inequality, which is that third one there, x squared, the absolute value of x squared plus x has to be less than or equal to the absolute value of x squared plus the absolute value of x, which we know is less than 4 plus 2 because x is less than 2 strictly, so x squared is less than 4 strictly. So we have the absolute value of x squared, which has to be less than 4, plus the absolute value of x, which has to be less than 2. So therefore, the absolute value of x squared plus the absolute value of x is strictly less than 4 plus 2, which is equal to 6, which is all greater than the absolute value of x squared plus x because of the triangle inequality. And then this is the last theorem in the chapter, 1.9. Let x, y, and a be in the set of real numbers. 1. x is less than y plus epsilon for all epsilon greater than 0 if and only if x is less than or equal to y. The second one, x is greater than y minus epsilon for all epsilon greater than 0 if and only if x is greater than or equal to y. 3, for the absolute value of a is less than epsilon for all epsilon greater than 0 if and only if a equals 0, right? The absolute value cannot be less than, 0. So for all epsilon greater than 0, the absolute value has to be less than epsilon, right? We're assuming that in our hypothesis. And I think these three I will go on to prove on Instagram because they're a little bit, unique, and it doesn't really they're just kind of out of the blue. They get really important for limits and defining epsilon neighborhoods. And so I think I will prove them in the Instagram. Okay, everyone, that's going to be it for today. Pretty short video. Thank you all for watching. Have a good rest of your day.